Ultra-thin whitetopping, or UTW, is a relatively new technique for resurfacing deteriorated asphalt pavements. UTW involves placing 2 to 4 inch concrete slabs on old asphalt pavement to form bonded composite pavements. UTW technique uses conventional concrete, shorter joint spacing, and bonding between the concrete and existing asphalt pavement. The first UTW experimental project was constructed on an access road to a waste disposal landfill in Louisville, Kentucky in 1991. The successful performance of this pavement has led to over 150 UTW projects in several states during the 1990s. With the use of UTW pavements increasing, the questions become how to repair the system when distresses such as cracking do occur, and would the repair and rehabilitation methods used for conventional concrete pavements be adequate for UTW pavements? UTW has been undergoing accelerated testing at Federal Highway Administration's Turner-Fairbank Highway Research Center in McLean, Virginia. 8 full-scale UTW test pavements were constructed during 1998 to study different combinations of design variables, including existing asphalt layer thickness after milling, concrete overlay thickness, joint spacing, and the use of fibers. The UTW pavements were subjected to accelerated load testing. Load testing using the Accelerated Loading Facility started in May 1998 and was completed in late 1999. The administration's project team has performed detailed distress surveys on a regular basis at each tested section. Some of the tested sections did exhibit cracking under loading as per the design plan. Other sections exhibited very little or no cracking. Major forms of distresses observed were corner breaks, transverse cracking, and longitudinal cracking. Faulting along longitudinal and transverse joints was also noted. During early 2000, it was decided to repair some of the cracked panels and subject the repaired sections to accelerated load testing. After a review of UTW repair techniques, the project team developed the repair plan. The plan was based on past experience with conventional concrete pavement repair. UTW panel removal and replacement was the most commonly used repair method. The process was broken down into 7 steps. Locate distressed slabs, mark periphery saw-cut lines, saw cut along marked perimeter and along joints, jackhammer interior concrete, jackhammer periphery concrete, prepare asphalt concrete base surface, and place and finish concrete. After locating distressed slabs, the next step was to mark the periphery saw-cut lines. The project marked lines 6 inches inward from joints. The UTW panels were sawed full depth along the interior marked perimeter. Then, to facilitate the concrete removal and to avoid damaging the surrounding panels, the joints were dry cut partial depth, about 1 to 1.5 inches. Next, the interior concrete was jackhammered. 90-pound hammers were used for the 6x6 panels, and 30-pound hammers were used for the 4x4 panels. The broken concrete was put in the bucket of a bobcat, then transported to a dump truck. The periphery concrete was jackhammered using only 30-pound hammers. This avoided disturbing the asphalt layer and the surrounding concrete panels. Crew members used a broom to sweep the exposed asphalt surface to remove rainwater and loose materials. This was followed by air blasting. The cleanup prepared the surface for concrete placement. The concrete placement included the following steps: concrete laydown, consolidation, finishing, texturing, curing, and joint sawing. A high early strength concrete, 3,000 pounds per square inch at 24 hours, was used. Concrete was delivered by truck and consolidated using a handheld spud vibrator. Next, crew members used a 10-foot-long straight edge to strike off the concrete. The straight edge was aligned in the longitudinal direction to match the existing pavement profile. The surfaces were then floated and bull floated, followed by edging to restore the joints between the repaired panels and the existing panels. Finally, burlap drag was used to create final surface texture to match the existing surface texture. Water-based white pigmented curing compound was applied immediately after the burlap drag. The specified coverage rate was 200 square feet per gallon. The repaired panels were then covered with plastic sheets. Joints were sawed to a depth of 1/3 of the panel thickness. Sawing width was 1/8 inch. The approximate time used for removing and repairing a 6-foot by 6-foot panel was about 60 minutes. For the 4-foot by 4-foot panel, the time was about 45 minutes. On-site quality assurance and quality control and specimen fabrication was conducted by Federal Highway Administration personnel. They performed air content test and slump test. The concrete had a slump of 1 inch and an air content of about 4.5%. The Federal Highway Administration staff also made cylinder and beam specimens. These specimens were stored and cured on-site for the first 24 hours and then transferred to a laboratory for testing and further curing. Compressive strength, splitting tensile strength, flexural strength, and modulus of elasticity were measured at 24 hours, 7 days, and 28 days. The repaired sections were tested between late April and early August 2000. By the end of testing, the repaired sections had been subjected to over 400,000 repetitions of 24,000-pound axle loading. This was well above the original design life of the test sections. Even though there was some cracking, the repairs performed well and extended the life of the original pavement. From the field operation conducted in this project, it appears that UTW panel removal and replacement using the evaluated procedure can be an effective UTW repair method. Additional technical details for repair of UTW are provided by a companion tech brief published jointly by Federal Highway Administration and Innovative Pavement Research Foundation.